Alright, we're going to work on converting between base systems. And so we're going to change numbers from base 10 into other bases. And base 10 is what we use. So let me get over here. And so we'll say we write in base 10. And we're going to change these into other base systems. Now, the nomenclature that your book is going to use is it will write a number in its form, so let's say, and then it'll write base 2 down below, or 2, I think and it writes it out in words. So, yeah, it says 2 for base 2. It puts the base in the basement in 2. Other books, other lessons, Khan Academy, some other places you might see, will write just the number 2. And it's meaning the same thing. That's the base of the system that we use. And so we're going to look at going from a base other than 10 to base 10, which is the system we use. And we're going to look at changing them. And so the base refers to the number of characters that we use in the system, and also the base we use in the positional system. So if I were to say there was a base 5 system, and then I'm going to write right to left like I normally write a number. The first position is 5 to the 0 place, then I have 5 to the first place, then 5 to the second, and so on as I add more digits. And this means that we have this as our multiplier. So just as I had 347 as 3 times 10 to the second plus 4 times 10 to the first plus 7 times 10 to the 0, I could, in a base 5 system, have a different value set. So in a base 5 system, 114 would be 1 times 5 to the second plus 1 times 5 to the first plus 4 times 5 to the 0, right? Because each position has a base 5 representation, and so this would be 1 times 25 plus 1 times 5 plus 4 times 1, or 25 plus 5 plus 4, or 34. So I write that as a base 5 system. 114 is equivalent to 34 in a base 10. And in base 10, we never write base 10. It's the system that we kind of reference to. So let's look at a conversion. I'll use the example that's on the lecture slides down below the video here. I have this number in base 8. Now base 8 is also called octal. Oct, like octopus, is 8, and octal is a base 8 system. And so we're going to convert this to base 10. And so this is the 8 to the zeroths, 8 to the firsts, 8 to the seconds, 8 to the cubes. So I have 4 times 8 to the third plus 7 times 8 to the second plus 2 times 8 to the first plus 6 times 8 to the 0. And 8, let's see, so this would be 6 times 1. I'm going to write right to left. 2 times 8 to the first is 2 times 8. 7 times 64. And let's see, that's 2, carry my 3, 512. And so let's work these out. That's 6, 16, 8, carry my 2, 448. And then an 8, 4, 2048. And now I'll add these up. I think again I'll continue. I'll go 8 plus 8 is 16, 12, 16, 22, 28, carry my 2, 6, 10, 16, carry my 1, 1, wait a minute, did I miss it? Oh, yep, carry my 1 and the 4, that's a 5. I missed a digit here, let me go back. Let's try this again. Let's see, 8 and 8 is 16, plus 6 is 22, plus 8 is 20, or 20 plus 6 is 28. Carry my 2. So 2 plus 4 is 6. 6 plus 4 is 10, 11. I don't know why I put a 6 in there, it's 11. And now I carry my 1, and let's see, 1 plus 0 plus 4, that's 5. There we go. Alright, it's probably better if I'm trying to carry my tables here where, and notice we're hinting at the algorithm that bases let us do, in that we can count in columns and carry over to create the new number. And that's the algorithms we use in base 10. Well, these algorithms exist in other bases also. But by focusing on the positional value, each position has the base to the power of the position minus 1. Right, so here's our decimal place. That's the first position, so that has the power of 0. That's the second position, as the power 1. That's the third position, that's the power 2. Fourth position, power 3, and so on and so on. And that's the same for all base systems. Alright, now to go the other way, to go from base 10 to a new base system, we're going to use division as our key. So let me take a number in base 10 system, our standard system, and put it into octal, which was used in old computers, which is base 8. So I'm going to take 299, and I want to convert it to base 8. And what I need to figure out is what my values are in base 8. I need to know my place values. And so I need to know 8 to the 4th, 8 cubed, 8 squared, 8 to the 1st, 8 to the 0. So 1, 8, 64, 512, and let's see, let's do that one more time, times 8, that's 6, 9, 496. If you play with computers a lot, you'll see these numbers pop up often because of how they're related to how computers work. And we'll see that a little more maybe when we look at some of the binary stuff. But what I need to now go is, well, 299 can't have anything in this place because it's smaller than that, nor can it have anything in this. So the first thing I have to do is I have to divide 299 by 64. And 64 goes into this 6 times. 6 times 4 is 8. No, 4. 6 times 4 is 4. Carry my 2. 2, 6. Alright. And let me do this again. 4. Carry my 2. 26. Yep. Now I'll do my subtraction. 5. Make sure was it 7? Nope, that's 36. I am off a bit. Let me just correct myself here. Alright. I'm thinking so what I looked at here, and I'll explain my idea here, is I know I'm looking at the 64th place, the 64th place, and if I multiply this by 5, I get something bigger than 300. And so I wanted to go down by 1, but I went up by 1, and it was just too big of a number, and I was looking at my multiplication going, oh, what did I do? But I like making mistakes in front of people because we can show how we fix them. When the math doesn't add up, when we don't see it adding up, we fix it. And so I know it can't be 5, so I'll try 4. 4 times 4 is 16. Carry my 1. 4 times 6 is 24 plus, and there we go. And so I get 3, and that's not bigger than 64. And so in my 64th place, I have a 4. But what's left over now is this 43. And so what I want to do with the 43 is I want to bring that over, and what's my next place? I did my 64th place, and now I have 8s. And so 8 goes into 43 5 times. 5 times 8 is 40. Subtract the 3, and so I have 5. So I finish my 8th place and 3. And so 453 in base 8 is equal to 299. Now, this is on the slides. I could have just followed the slides, but I like showing the decision process, and I'm glad I made a little bit of a mistake, because mistakes are going to happen when we do mathematics, and how we fix them is important. How we get a feel for what our numbers should do is an important part of this. And for me, I was looking at 60 times 5 is about 300. And since that's going to be more than this, I want to check the next number down. And that's kind of why we study estimation a bit sometimes, is to figure out how to work our way through these things. All right, play with the converting bases problem in the homework, and I think, I remember my son Sam, on his 6th birthday, I gave him a cake, and I put those candles on top of it, because in base 2, well, what would base 2 get? We get the 1's place for 2 to the 0, we get 2 second, and 2 to the first, and 2 to the second. And so we have 1 times 2 to the second, plus 1 times 2 to the first, plus 0. And so that's 4 plus 2 equals 6. And that's what I put on his cake for his 6th birthday. It was 110, which is in binary, which is our computer-based language. And I think I put a couple questions on the homework about binary. And we'll see in the notebook problem where we look at how we can do multiplication in binary in a very quick fashion, for computers at least. All right, and this is a short little section. These sections are kind of compact, and I'll see you on the other side as we continue to explore the power of positional value.